All right, folks, let's start. Last time we were working on this circuit. You'll be doing a lot more with this circuit on the problem set, as you've probably realized by now. I just want to recap a couple of points that I mentioned near the end of the lecture, just so we get the right picture. We developed the differential equation for this circuit, which was RC YC dot. And remember, last time we considered the voltage across the capacitor as our output, and the voltage source here as the input. In the problem set, you'll consider the case where the resistor voltage is also one of the outputs. So here we had RC and we had YC was X. And we worked this out. We let X be a complex exponential. And we recognized, given that the initial capacitor voltage is 0, that the capacitor is uncharged, we have an LTI system. And the frequency response for this particular output we call H sub C. Plug it in here. You get a derivative of y is I omega times H times E times H times the complex exponential plus the output itself equals the input. And our standard trick is that well, it's not a trick, really. We get rid of the e to the I omega t because that's just the phasor going around the unit circle, so it's never 0. So we can get rid of it. And then when we solve for HC, we get 1 on the right-hand side. And on the left-hand side, we get I omega RC plus 1. Now, I massaged this a bit near the end of the lecture. I took out the RC. So you'd have a 1 over RC here. And then you'd be left with I omega plus 1 over RC. And then we made a connection with an earlier example that we had done, where we had looked at, so previous example, h of t being e to the minus a t u of t. And what did we get for the frequency response to that filter? One over a plus I omega. This is one of those time domain, frequency domain pairs of functions that you'll be using a lot, and you'll practically memorize as we go through the course. Now, when you compare this with that, how are they related? What if I scale this by A? If a system that has frequency response H has frequency, if a system that has impulse response H given by this expression has frequency response equal to this, then what is the frequency response of a system that has this as its impulse response? Huh? A. You just multiply this by A. If you're multiplying the time domain by A, you have to multiply in the frequency domain by A. And that's because of the fact that H of omega is defined as the integral from minus infinity to infinity of h of t e to the minus I omega t dt. And integral is a linear operator. So if you scale this h by a, that a just comes out. Okay? So that's why when you scale a function in the time domain, its corresponding frequency response, or as you'll learn later, its Fourier transform, will get scaled and vice versa. So now compare this with that expression. And what can you tell me about, so what is hc of t? E to the negative t over RC. Yeah. U of t. Yeah. Scaled by 1 over RC. So notice, even though we haven't really studied, in fact, studied the inverse Fourier transform relationship. Last time I said, we've given you a way of going from the time domain to the frequency domain. The inverse of this relationship we haven't learned yet. That's going to come later. So in general, if I give you a function of omega, at this point, you won't be able to go back to the time domain. But in this case, doing some simple pattern recognition, you can do that. So this is the impulse response of the RC circuit when you consider the input voltage source as its, or the voltage source as its input, and the voltage across the capacitor as its output. Any questions? All right. Oh, brother. There's a surprise behind every board here. Let's see if there's an iPod here. So one thing I want you to notice about this system is that its input-output relationship is described by a linear constant coefficient differential equation. So the circuit is an LTI system, is an example of an LTI system characterized by, or continuous time LTI system, characterized by a linear constant coefficient differential equation. We call these LCCDEs as well, because from the context, it's always clear whether we're in discrete time or continuous time. In discrete time, this would be a difference equation. Systems that are representable or characterizable by a linear constant coefficient differential equation, just like their discrete time counterparts, will have frequency responses that are rational. In discrete time, they were rational in terms of e to the I omega, so you always lived on the unit circle. But in continuous time, the polynomials are in terms of I omega, not e to the I omega. So h of omega will be a polynomial b over a. This will be in general an nth order polynomial in I omega. And this will be an nth order polynomial in I omega. In this case, the numerator is a zeroth order polynomial in I omega. There's only a constant term. And the denominator is a first order polynomial in I omega. So always keep the I omegas together. I and omega, keep it together when you're writing these expressions. In E40, if you're taking that, or if you take it next semester, you'll see sometimes the letter S used instead of I omega when they're figuring out the frequency response of a filter. You'll learn about this S business in EE120 thoroughly. S is basically a variable that's in the complex plane. So this is real, this is imaginary. But when you want to evaluate the frequency response, you live on the I omega axis. So this is the I omega axis. Okay? Just as in discrete time, you lived on the unit circle and you went around it to figure out what the frequency response is, magnitude, phase, and so on. For continuous time systems, you go along the I omega axis. We did this last time. So S in general actually can be a complex number. Sigma plus I omega. It's got a real part and an imaginary part. Except when we evaluate the frequency response, we set sigma equal to 0. So we live on the I omega axis. Now let's break this open a bit. Whoa. So suppose I have a differential equation, a n d to the n y over dt n plus a n minus 1 d to the n minus 1 y, it's y of t of course, over dt to the n minus 1 plus a1 dy dt plus a0 equals, and then I go on the right side, I have bm d to the m x over dtm plus all the way to b1 dx dt plus b0 xt. And this is, of course, yt. Sorry. xt. So this is a linear constant coefficient differential equation, the most general form you'll find. You can, again, without loss of generality, always assume that this an is 1. Because if it's, first of all, if it's 0, then it's a lower order differential equation to begin with. Just starts, you assume that's n. And if it's non-zero, you can divide both sides by an and rescale all the coefficients. So, but I'll keep it in there just for aesthetic reasons. Now, how do you figure out the frequency response to this differential equation? What did we do in this case? Plug in e to the I omega t. And then y of t is simply the frequency response times e to the I omega t. And what are the derivatives of these two sides? X dot is what? I omega e to the I omega t. So until you get to d to the m xt dtm, and that's what? I omega. Remember, keep the I and omega together. I omega to the m, e to the I omega t. See, that's how you get the polynomial in terms of I omega, because every time you differentiate, an I omega comes down. In discrete time, you didn't have a differentiation, you had delays. So every time you delay, there's an e to the minus I omega that shows up. And on this side, you have y dot equals I omega h omega e to the I omega t, all the way to the nth derivative which has an I omega to the nth power h omega e to the I omega t. Now I want you to plug these into that differential equation. Don't bog yourself down with the math. It should be fairly easy because of the pattern. And tell me what the h of omega is for this system. You have all the coefficients. These are assumed to be known. And you now have expressions for each of these derivatives. So just write it out and tell me what h of omega is in terms of a ratio of a polynomial in I omega over another polynomial in I omega. Do we have a Danny in the class? No Danny in this class? Okay, Meatball. Do your gig. A little louder. So, you mean this one? Okay, so this is remember, this is the left side of our differential equation. This is the right side of our differential equation. This by itself is not a differential equation. It's that equals this that makes it a differential equation. So, now let's deal with the left-hand side. What have we got, Meatball?
We've got an
an I omega to the power n h omega. Well, let's not just do that. Okay. Yeah. So an I omega to the n minus first power plus a1 I omega plus a0. And then on the right-hand side, with the b to the m. B. Okay, that's what we got. When you plug it all in. And then, what's the next step?
We're going to try to solve for h omega. So first of all, we're going to cross out h omega on both sides.
These two go away. And then we solve for h omega. So that's a ratio. That's good. We want a rational function. And what's in the numerator?
The numerator is b to the n I omega m, that whole thing.
It's this whole bracket. Goes in the numerator. Bm I omega to the m plus, let's skip that. Dot, 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 plus b1 I omega plus b naught. And in the denominator you have an I omega to the n plus see, so we have a polynomial in terms of I omega in the numerator and a polynomial in terms of I omega in the denominator. If we want our system, and the order of the system which is the order of the differential equation that characterizes it, is the larger of n and m. The side that has the highest order derivative, that's the one that governs the order of the system. Now, you might say, okay, what is all this order business? In discrete time, what was descriptive of the order? What determined the order? When I had a difference equation. The biggest? Delay. In discrete time, when you had, for example, y of n equals alpha y of n minus 2 plus x of n, you looked at all the terms, and the one that had the largest delay determined the order of the system. So this is second order. Largest delay is 2. Therefore, you need 2 unit storage elements. And therefore, the system is second order. Okay? So the elements of memory, the number of elements of memory you need, determine the order of the system. So in this difference equation, you need 2 unit storage elements, so it's a second order system. Now let's go back to our circuit. You have, in our RC circuit, you have, where is it? RC y dot plus YC. Let's get rid of this time dependence here. YC equals X. Okay? The highest derivative belongs to the Y in this case, and it's 1. And we're claiming that this is a first order system. In continuous time, the memory elements are things like capacitors, anything that has an integrative feature. And the way we find that is you integrate symbolically. You don't actually carry out an integration. You integrate symbolically both sides. How many times do I have to integrate so that I no longer have a derivative? Once. So I have RC y plus integral YC equals integral X YC. And so what this says is YC is minus 1 over RC integral YC plus 1 over RC integral X. YC equals integral YC times, so it's minus 1 over RC times, and then integrate it. Okay? So YC is obtained by multiplying it by minus 1 over RC and integrating it, and adding to that 1 over RC of X and integrating that. Okay? YC is obtained by multiplying it by minus 1 over RC and integrating. And then adding to that the 1 over RC times X and integrating. How many integrators do I have? That's the storage element. So these integrators are the memory elements. Integrators are the storage elements for continuous time. And they represent, the number of them represents the order of the system. So number of storage elements represents the order of the system. Now, if I didn't have this minus 1, I would have easily merged these two together, the 1 over RCs. So you can actually redraw this to make it look cleaner. So you have 1 over RC. X goes in here. You add to that a minus 1 times YC. So you reverse the polarity of YC. This is an arrow. So you have minus YC times 1 over RC integrated. So that takes care of the Y term on the right-hand side. And then here you have X times 1 over RC integrated. This is called a delay adder gain block diagram, both of these. Delay adder gain block diagram representation of this system. Just like the integrator adder gain. Phew. Integrator adder gain block diagram. Integrator adder gain block diagram, which is the cousin or the counterpart of the delay adder gain block diagram for discrete time systems. In discrete time, storage elements or delay elements were our memory elements. In continuous time, it's these integrators. You typically do not want to implement systems by differentiation. Can anybody guess why? Why do you not want to implement systems using differentiators in the real world? The more, think in terms of noise and accuracy. Yeah. You remember one of the things I said is real-world systems respond to the areas under the input signals. The areas under the signals are the determining factor. And integrating a function over some finite interval gives you a more accurate. So if all my signals had been smooth, no problem. Differentiation and integration theoretically should be okay. But in the real world, you have all kinds of noise. So instead of a nice looking signal like this, you're going to have notice how unstable differentiation will be. Going from point to point, it flips wildly. And that's not what you want. Whereas if I integrate the same red signal over some interval, the fluctuations in that integral will kind of average out. So I have a much more stable, numerically stable calculation. So that's why we implement systems using integrators. And a capacitor is a great example of an integrator. A capacitor has as its well, I shouldn't. Let's use a different. 1 over C, I'll use regular English, current, tau, the tau, from minus infinity to t, is the voltage at time t. So the current through a capacitor from minus infinity to t. If the capacitor is uncharged at time 0, then obviously you can toss out this minus infinity to 0 interval. So the voltage across the capacitor at time t is the integral of the current times 1 over c. So the capacitor acts like a very nice integrator, an analog integrator. Okay, let's take a break. If there are no questions. Yeah. Yeah, because the differentiator fluctuates. The output of the differentiator will fluctuate wildly as I go from time instant to time instant. because of the wild fluctuations of the red signal. Notice sometimes it's going up, sometimes it's going down within a very short time interval. But when I integrate the same signal, those fluctuations around that smooth average out. So I get a much more stable operation. Yeah?
Does the integrator block diagram, like adder
Integrator.
gain block diagram, does that fit in the same place that the delay adder gain block
Yeah.
diagram fits into the chart?
Right. This block diagram fits exactly in the same place that the delay adder gain block diagram fit. So you should be able to go from the from the integrator adder gain block diagram to the differential equation. I should have first asked if there are any questions before giving the break. So you should be able to, if I give you a delay adder gain or integrator adder gain block diagram, you should be able to write the differential equation. Well, you first write this equation, and then you differentiate as many times as necessary until you get rid of all the integrals. From that, you should be able to figure out the frequency response. From that, you should be able to plot the magnitude response. So they're all connected, and these are the dots that you need to connect when you go home. All right, take a break. Let's see if I can cover what you need to finish the problem set by the end of today's lecture. I doubt it. There may be some leakage into Thursday of stuff you need. Well, let's see where we get. So the next topic I want to talk to you about is interconnections of LTI systems. There's this book that I got recently that I've started reading called Music of Life. It's written by one of the pioneers of the Genome Project. And he's talking about how biologists have, for the past 100 years, been tearing apart Humpty Dumpty, and now it's time to put them back together again. What he means, of course, is that you've got all these micromodules that you've analyzed to death, but how do they all fit together in larger systems? One of your jobs when you get out into the real world is to analyze complex, usually large-scale systems in whatever area. There may be engineering, finance, biology, law, whatever. You always have to be able to see what the modules are. So when you see a large system, you should be able to break it down into its components, figure out how the components work. And then the next stage is how do these components fit together to make the larger system behave the way it does. And therein lies the art. What level of fine-grained analysis do you do? Of course, we have a much humbler objective here. The kinds of interconnections that we're going to discuss are fairly straightforward. And there are essentially three of them. We have cascade or series interconnections of LTI systems. We have, actually before that, the simpler one is parallel. And the one that's more interesting is feedback. These are the three structures that I want to talk about. Some of these I'll go over much faster than others. So what do I mean by a parallel interconnection of LTI systems? A parallel interconnection is when you have an input signal that goes into two systems, H1 and H2, in parallel, and the outputs of those systems get added to produce Y. These are, of course, both LTI. Now, in the textbook, for all of these interconnections that I talk about, there is proof that if you put these LTI systems in these configurations, the overall system, you can think of this as a more complex system, H1, H2, let's call this H. The more complex system is also LTI. I won't go through the proof of that. It's kind of secondary in importance. What I want you to get is how to read these diagrams and write down the equations that govern these systems fairly quickly. So if I have an input that's going into H1, what's the output here? If I call it Y1 and this Y2, what's the output with respect to X and H1? Huh? H1 not convoluted with, convolved with X. Let me get my gun. And the other one is H2 star X. And so the overall response is simply H1 plus H2 star X. Convolution has a distributive property over addition that's easy to prove if you just plug it into the definition. So a parallel interconnection of two or more, you can extend this to more systems in parallel, of course, simply gets you to add the impulse responses. So the overall impulse response, this must be the overall impulse response of the system H. And what can you tell me about the frequency response? So H is H1 plus H2. Let's put the T's in there now. alternatively, you can write h1 plus h2 times t. And what's h of omega? h1 plus h2. It's so straightforward, I don't even need to do an example of this. Again, this linearity comes from the fact that h of omega is the integral. Remember, h of omega is the integral of h of t e to the minus I omega t dt. But if h is the summation of these two, then you have h1 plus h2, the whole thing e to the minus I omega t dt. And that obviously is the sum of the two frequency responses. So that's the tamest of them all, parallel interconnection of LTI systems. There's a whole area of signal processing where they talk about filter banks. You have a whole parallel set of filters that take the same signal, for example, an audio signal, filter out different frequency regions, and then do different things on different branches, and then they all put them back together again. The next configuration is cascade, or series. That's when you have H1 and H2 in this kind of a configuration. Okay? So if the intermediate signal is Y1, can you tell me what the... Don't blurt it out. Let everybody think for a few seconds. If this is my H, the system H, or what's H? What do you think the frequency or the impulse response is of the configuration? Think about it. It wasn't meant to require this much work. What are we doing exactly? What is Y1 in terms of X? Y1 is X omega. We're in the time domain, my friends. My friends, we're in the time domain. X star. Never mind, let's get back to work. X star H1. And then Y is what? Y1. Well, let's put it this way. Yeah, Y1 star H2. But Y1 is X star H1, so it's X star H1 star H2. And there's this nice little property that if you've been doing the reading, you would have seen by now. It's the associative property of convolution. You take two of those three and bunch them together, and this must be H. So it's X star H, which means the impulse response of the overall system is the convolution of the individual impulse responses. Does it matter which system comes before which one? Very good. And what do you think the frequency response will be? Well, we're hearing conjectures that the frequency response will be the multiplication of the individual frequency responses. Let's see if that works. How do we verify that? Complex exponential. You plug in a complex exponential at the input. So if x is a complex exponential, then y1 is what? h1 of omega e to the I omega t. And if y1 is going into the second system, then what is y? This is a complex exponential multiplied by a number. This doesn't have a time dependence. This is just a number. Happens to be a complex number, but so what? So if this h1 had not been there, and I just plugged in an e to the I omega t into h2, what would come out? h2 omega e to the I omega t. But I'm not sending e to the I omega t. I'm sending a scaled version of e to the I omega t. So what comes out? Scaled version. And so this must be h of omega. Now, there's a problem that I've placed on your homework where you multiply finite order polynomials, and you're supposed to discover that when you multiply two polynomials, the coefficients of the product of those two polynomials are obtained by convolving the individual coefficients of the two polynomials. Now, try proving that with techniques in math. You'd have to do some kind of induction, keep the degree of one fixed, and then try it the other one for order n, assume true for order n minus 1, and then prove true for order n, for a higher order. It's a pain. But if you use signal processing techniques using convolution, it falls out just like that. And so it's important to keep this in mind for discrete time systems. I've walked you through that problem in the problem set. But essentially, the upshot of that problem is you get a polynomial of order n, a polynomial of order m, you multiply them. You get a polynomial of order n plus m, and the coefficients of that new polynomial are obtained by convolving the individual coefficients of the two polynomials that you multiply. And you get it by this relationship, that convolution in time is multiplication in frequency. That's one of the golden rules of this course. Convolution in time is multiplication in frequency. It turns out that the dual of this is also true. Multiplication in time is convolution in frequency, but there's a caveat there that we'll get to when we study Fourier transforms. But for now, all you know is that convolution in time is multiplication in frequency. Okay, so that's that. Now we get to feedback. So here I have a system F with frequency response F and impulse response small f. I take y, I send it through another LTI system, G, and I mix it with the input signal. Now you've got to be careful. Very often these will have opposite signs, and if they do, they'll be specified on the diagram. So I may say this is plus, this is minus. But if I don't put anything, like I'm about to do now, you assume both of them are plus. So this is your overall system. Call H. Okay? Yeah?
Does mix necessarily mean add, like always?
Yes, this is an add. This is always an add for a feedback configuration. Well, add or subtract, but it's not a multiplier. So again, in the textbook, you'll see a proof of why if this is LTI, the overall system will be LTI. We won't go into that. But what we care about is, okay, it's LTI. These have frequency responses. What can we say about the frequency response of the overall system? Now, this is trickier than the other two because you've got to be careful. But if you follow the signals around the loop, you'll see that it's not that difficult. So assuming that this system is LTI, the whole system, and I plug in x of t is e to the I omega t, then y of t will be h of omega e to the I omega t. Okay? Now, so I'm taking h of omega e to the I omega t into this LTI system. What's going to come out? G of omega, h of omega, e to the I omega t. Right? If x is a complex exponential, y is h of omega e to the I omega t. And I'm taking that signal and sending it back through this system G. So the output of this system is g omega h omega e to the I omega t, for the same reason that we just dealt with the cascade structure. So I have e to the I omega t plus this. So let's label this signal. This signal is e to the I omega t plus g h e to the I omega t. G h. Can you read it back there, or is it too small? It's too small. You should always yell if I do that. Write it with the big chalk. So the signal here is e to the I omega t plus g omega h omega e to the I omega t. And you can write this as 1 plus g omega h omega e to the I omega t. Okay? So again, I have an e to the I omega t times some complex number. Now that's going into F. It's just bookkeeping. You just go around the loop once and you're done. So I started here, and I've been going around the loop. H omega e to the I omega t goes into G, just gets multiplied by g omega. Gets added to e to the I omega. That's that. So the signal going right into F is 1 plus gh times e to the I omega t. When it goes through F, what comes out? F omega times 1 plus g omega h omega e to the I omega t. But that must be equal to what? H omega e to the I omega t. Because they're the same signal now. I'm in the same place. Now solve for h omega and tell me what you get. You want to go for it? Talk it through, but more quickly than usual.
All right, so first I just distributed F omega across.
Well-
Okay, cross out the E side.
Cross out the e to the I omega t. Okay? And then you distribute the f across. So you've got f of omega plus f g h. And that's equal to h of omega.
And then I moved the second term on the left side to the right side because that has H of omega.
Right. So we take to one side all the terms involving h of omega. And when you do that, what do you get? Something times h of omega. What is that something? 1 minus f g. And on the right-hand side, you have f of omega. So h of omega is f 1 minus fg. Does everybody agree with this? This is called Black's formula. He was an engineer in the earlier part of the 20th century. He's the guy who solved the problem of how to send signals from the East Coast to the West Coast and deal with the degradation that the distance, the large distance, caused, using feedback. And this Black's formula is very easy to remember. The frequency response of a feedback configuration is the forward gain, the gain of the forward loop, over 1 minus the loop gain. If you look at this loop, what's the interconnection of F and G when you go around the circle? The cascade. 1 minus the cascade. So it's the forward gain equals, let me write that name somewhere else. And this is forward gain over 1 minus the loop gain. Loop gain is simply the gain you see when you go around this loop. So when I go around this loop, F and G appear to be in cascade, and that's why the loop gain is F times G. Be careful, if you had a minus sign here, what would happen in the final expression? It would be a plus down there, because that minus 1 will also be in the loop. So it would be F times G times minus 1. Let me write that explicitly so that we don't forget. So if I had plus minus G F like that, then the forward gain would have been F, and then you have 1 minus the loop gain. So this is forward gain, loop gain, which would be 1 minus, and the loop gain is minus 1 times F times G. Because this minus 1 acts like a scaling block in that loop. And then you'd have F in the numerator. So you'd end up with F over 1 plus Fg. Now, feedback has many, many applications. And I will just do one example of that in the time that remains. No way you can track that in this configuration. Yeah. Very very hard. So when we talk about the feedback, you've got to figure out either its frequency response or somehow the differential equation and then go from there. Okay, so let's do a discrete time example. We had the example of the form 1/2 to the n or alpha to the n u of n as an impulse response. And you figured out in a previous lecture that the frequency response of this is what? This is another one of those forms that you need to get familiar with. Alpha to the n u of n, when alpha is less than 1, in other words, it's inside the unit circle. In this case, I have a 1/2. Corresponds to what? 1 over 1 minus alpha e to the negative I omega. So in this case, it'll be 1 over 1 minus 1/2 e to the minus I omega. Now suppose I take this system. Suppose I take this system and place it in a feedback configuration. I think I just need one more board before I'm done. So let's say I take that system F and I put it in a feedback configuration involving a delay and a multiplication by beta. Okay? What's the frequency response of this delay? If I have a signal x of n going in to a delay, and what comes out is simply a unit sample delay, what is the frequency response of the system? No. E to the negative I omega. So this system, G of omega, is e to the negative I omega. Plug in x of n equals e to the I omega n and see what comes out. That's how you go from difference equations to the frequency response. For every delay, you have an e to the minus I omega. So there's an e to the minus I omega here. That's my G. So what's the overall frequency response of the system? H of omega. What's the forward gain? F of omega over 1 minus, what's the loop gain? F times e to the negative I omega times beta. So 1 minus the loop gain, which is beta e to the minus I omega, f of omega. Well, now let's plug in that, that f of omega. You have 1 over 1 minus 1/2 e to the minus I omega divided by 1 minus beta e to the minus I omega over 1 minus 1/2. And when you simplify this, what do you get? 15 seconds. Hurry up. We got people waiting outside. The denominators go away. I'm left with 1 over 1 minus 1/2 minus beta. 1 minus beta plus 1/2 e to the minus I omega. Now, if beta is a switch, if I have a choice of what to do with beta, can you turn that low-pass filter into a high-pass filter? Can you do that? What do you do with beta? Give me a value of beta that will make this a high-pass filter. Negative what? No, it can't be negative 1/2. That takes that x to the origin. So it's got to exceed 1/2. So if it's, let's say, minus 2/3, then this will turn into a high-pass filter. So you've already built 1 million of these low-pass filters, and your boss says, okay, with just simple gadgets and off-the-shelf equipment, build me a high-pass filter. You put it in this configuration, and you've got your high-pass filter. We'll carry on next time.